today is the last day, and we have a speaker, George Dangic, which is going to talk about thermal conductivity, which is related to anharmonicity, so it's a very interesting topic, very much related to the argument of this school. So, without other introduction, let's go to the talk. George.
We have a clicker problem.
Magia.
So welcome everyone for the last day. So yeah, today we are going to do some exercises for the most recently implemented module in SSCHA, which is the calculation of the thermal conductivity. And because we are using SSCHA, we are going to focus mostly on the thermal conductivity in strongly anharmonic materials. So yeah, the outline of the talk is to give the brief introduction in why would we care and why should we calculate lattice thermal conductivity in these materials. Then we are going to talk about the most common way of calculating lattice thermal conductivity in the materials, which is a Boltzmann transport equation. Then we are going to continue by introducing a new way of calculating lattice thermal conductivity, which is a Green-Kubo approach that is implemented in SSCHA. And then I'm going to discuss some details about the SSCHA implementation, which is going to be useful for the hands-on session, which is after the coffee break. So let's start with the introduction. So we are going to talk about lattice thermal conductivity. So the part of the thermal conductivity, which is mediated by phonos, and we are going to denote it by kappa. So the lattice thermal conductivity is basically the constant of proportionality between the heat current in the material, which is subjected to some thermal gradient. So this is a Fourier law. And lattice thermal conductivity is this factor of proportionality. So why would we care about it? So we care about it because it impacts the technological applications of materials. So some materials have different technological applications based on their lattice thermal conductivity. A lattice thermal conductivity being too high or too low prevents some materials to be utilized to the best of their potentials. And in the technological application, we usually worry about extremes, so either too high or too low thermal conductivity materials. So for example, if we have a material with very high thermal conductivity, we might want to use it in the thermal management. So that means if we have a device that works and obviously dissipates heat, if we left it to its own devices, this dissipated heat would increase the temperature of the device, which would lead to deterioration of the performance of the device. So you want to take that heat out as quickly as possible, and for that you would need very high thermal conductivity materials. So for technological applications, the most commonly used materials for this type of thing are metals, so aluminum or alloys or copper. And in these materials, because they are metals, the most heat is conducted by the electrons. So the electrons carry the most heat, and the electronic part of the thermal conductivity is the one that's relevant. However, the materials that have even higher thermal conductivity are insulators. Most famous are diamond. So the diamond is one of the materials with highest possible lattice thermal conductivity, and newly discovered boron arsenide, which has even higher latticemal conductivity than diamond. So this is these materials are insulators, as we know, so the electrons do not play any part in the conduction of the heat, and thus the most heat is carried by the lattice vibrations or phonons. On the other end of the spectrum, we have the materials with low lattice thermal conductivity, and why would we want to use them? So we want to use them for the thermal insulation. So we want to keep the heat inside the system or keep the heat outside of the system. For example, in the internal combustion engines, we know that the efficiency of the engine depends on the temperature that we are burning fuel on. So for example, in the airplane industry, you want to insulate the engine so you increase the temperature of it and you don't burn the passengers. And to insulate the engine, one has to use very light material, very thin material, which means that we need a very low lattice thermal conductivity materials. Another reason why we want low lattice thermal conductivity is in the thermoelectric materials. So the thermoelectric materials are the ones that are converting directly the heat to the electrical energy or vice versa, so the electrical energy into heat. And the efficiency of these materials is proportional or governed by this thermoelectric figure of merit, which we denote by ZT. And ZT can be calculated with this formula here. So as you can see here, the ZT or figure of merit is inversely proportional to the lattice thermal conductivity. So if we decrease the lattice thermal conductivity, we increase ZT and we increase the efficiency of the thermoelectric materials. So which materials could have low thermal conductivity? Well, the first guess is we need them to be insulators because we want to minimize the electronic part of the thermal conductivity. So what type of insulators will have low lattice thermal conductivity? Well, the best guess is the highly anharmonic materials. Why? Because highly anharmonic materials have a large scattering between phonons, and the large scattering between phonons leads to low phonon mean free paths, and the low phonon mean free paths lead to low lattice thermal conductivity. Also, another way of reducing the lattice thermal conductivity is to make a material amorphic, so to break translational symmetry, and that leads to the scattering of the vibrations, and then leads to low lattice thermal conductivity. So, to show the importance of the anharmonicity in the lattice thermal conductivity, we have this plot here from this publication. So on the x-axis, we have the anharmonicity measure. So if this number increases, the anharmonicity increases. And then in y-axis, we have the lattice thermal conductivity at room temperature. And as you can see, there is a pretty linear dependence between anharmonicity and the lattice thermal conductivity. So if we increase the anharmonicity, the lattice thermal conductivity goes down. And here we have like one of the some materials that exhibit very low lattice thermal conductivity. And we can see that they are mostly belonging to some common space groups. Okay, so how do we calculate lattice thermal conductivity? Well, we have two most common ways to calculate it. One is using the lattice dynamics and then Boltzmann transport equation. We will mostly focus on this part, and we are going to talk extensively in the next slides about this. But there is another method that we are not going to discuss today, but we are going to mention it a few times in passing, and that is the molecular dynamics, or MD. So molecular dynamics is basically you make a block of the material, and then you solve the Newton's equations inside of it. So you move the atoms or constituents of that material according to the Newton's equations. And then you calculate forces whichever way you want. So there is two ways of calculating lattice-thermal conductivity in MD. One is the direct method, which is basically just reproducing the experiment in the molecular dynamics simulation. So you make a very long piece of very long simulation cell, then you take heat from one side or from the edges of your simulation cell and put it inside in the middle, which basically creates a heat current from the ends to the middle, and then you know the heat current, and that heat current will generate a thermal gradient, and then you can calculate the lattice thermal conductivity just as you would do it in the experiment. And the second part is using the Green-Kubo relations and calculating lattice thermal conductivity from the fluctuations of the heat current in the equilibrium MD. So as I said before, we are going to focus on the lattice dynamics method. So what I mean by lattice dynamics method is basically using a phonon or phonon-like picture. So you take your Born-Oppenheimer energy surface, you expand it in the Taylor series, and then you do the perturbation theory or whatever to actually get the heat current and calculate lattice thermal conductivity. Okay, so let's try. So as I said, when we do lattice dynamics, we use Boltzmann transport equation to calculate lattice thermal conductivity. And this is actually now implemented in SSCHA. So let's briefly discuss this method. So in the Boltzmann transport equation, we imagine that the heat is transferred by the weakly interacting phonon gas, which means that the phonons are well-defined particles. So basically, we imagine them as being gas particles that diffuse through the material. Then we take a look at the particular phonon state and the population of the phonon state, here denoted by the NQS, and we track its change in time. So why would this phonon population change in time? So there is three main reasons. So the first reason is diffusion, so passing of the phonon gas through some through that state, and we can say that this change in time is basically depending on the position of that phonon wave packet, and then using just the chain rule of the derivative, we can change this derivative over time to derivative over space, and then we have the phonon group velocity because we have here derivative of position over time. And then why would population depend on the position of the wave packet? Well, we know that this does not actually in the equilibrium depend on the position, but it does depend on the temperature or at that position. So we can actually substitute here NQS as the equilibrium NQS, and then use again chain rule to actually describe this derivative over time as a derivative over temperature with the gradient of the temperature. So okay, this is the diffusion part. Then the second part is we can have a change of phonon population due to some external field, but the phonons are not charged particles, so there is no field that we can apply to actually influence it. So this part we don't care about. And then the third part, which is probably the most troubling, is the scattering. So the phonon population of this state changes due to the scattering between phonons, but what we do here is to linearize the Boltzmann transport equation. So say that if we have some excited population of the phonon, NQS, it will relax to the equilibrium population, NQS naught, in some characteristic time, tau QS, which is characteristic for each phonon mode, and this characteristic time we are going to call the phonon relaxation, phonon lifetime, or the relaxation time of the phonon population. Okay, and then in the steady state, we know that the change of the population of phonons with time should be 0. Then we equate everything to 0, and then we get the expression for our population of the phonons. So what we do next is just inserting this expression into the heat current definition. So the heat current here is defined as this expression. We will not derive this part, but this is the definition of the heat current. As you can see here, we need phonon phonon frequencies, phonon group velocities, and the phonon populations. So instead of phonon populations, we write this one, and we disregard the constant term. And then by matching terms with the Fourier law, which we already showed, we can get to the expression of the lattice thermal conductivity in the Boltzmann transport equation. As you can see, we need phonon frequencies, phonon group velocities, and the phonon lifetimes to calculate the tensor of the lattice thermal conductivity. Now there is, how do we calculate the phonon lifetimes? We're not going to go into detail here, but one can use the perturbation theory, the first order perturbation theory, to get these phonon lifetimes. So this is what is implemented in most modern codes that calculate the lattice thermal conductivity. Okay, so what does this all mean? So there are a number of approximations and assumptions that we made during this derivation, and we are going to discuss one part of it now, so we can introduce the next method. So from this discussion above, we can see that we kind of assume that the phonons are well-defined quasi-particles. So they have a population, they have a they have the population number, they have frequencies, lifetimes, and velocities. But is that true? So if that was true, then the displacement correlation function that we discussed several days before will be some decaying oscillations. And then the Fourier transform of it would be Lorentzian, which we already, again, discussed. So this is nothing new for you guys. And obviously, the line width of that Lorentzian profile is related to the phonon lifetimes that we have. So this Fourier transform, or the correlation function, it has been shown, again, in the past few days, that it is related to the scattering cross sections. So either in the scattering cross section, either in the Raman or neutron scattering or the X-ray scattering, and it's also related to the signal in the infrared experiments. And this is true for the low anharmonicity material. So here we have a figure from this reference. I think this is silicon, which is highly harmonic material. So the anharmonicity is quite low here, and this is high quality sample. So this picture is valid. And as we can see, these peaks can be fitted almost perfectly with the number of Lorentzians, right? So in the silicon, we know that this picture holds, and this has been proven by numerous first principles calculations that predict lattice thermal conductivity in silicon quite well. But silicon is not really interesting. It is interesting from the technological perspective, but there's nothing interesting about lattice thermal conductivity of silicon. However, there are some materials that we care about their lattice thermal conductivity, and those are, as I said, thermoelectric materials. One of the most famous one is the light telluride. It has a very high thermoelectric figure of merit. And if we do the same type of experiment or similar type of experiment for light telluride, we see these satellite peaks appearing in the signal, which is evidence of the highly anharmonic material. So here we have this the signal from the lead telluride, and as you can see, there is a peak, and this figure has been shown multiple times during this school, but just in as a first principle calculation. So what do we do if we have this this non-Lorentzian and anomalous line shapes? Now, it's not just lead telluride that has these features. It is pretty common feature of all highly anharmonic materials to have these non-Lorentzian line shapes. And additionally, they are especially pronounced close to the structural phase transition. And indeed, lead telluride is known as the incipient ferroelectric. So at very low temperatures, there is a bit of a debate whether the lead telluride actually belongs to the space group that people usually assign it to. And as you can see, at low temperatures, it has this double feature, but as you increase, it becomes more cubic, and this anharmonic feature disappears. So, meaning that as you increase the temperature, you would assume it becomes more anharmonic, but also when you increase the temperature, it goes away from the phase transition, so it becomes more harmonic. So, yeah, it is kind of weird trade-off type of situation. So, yeah, it is this anharmonicity is especially pronounced close to the structural phase transitions. And as you can see, because it has these double peaks and does not have the Lorentzian line shapes, it cannot be regarded as the good quasi-particles, meaning they do not have well-defined phonon lifetimes, and then do not have the well-defined phonon frequencies or population numbers. So what we can do in this case, well, we can give up on the Boltzmann transport equation altogether and run Green-Kubo MD or direct MD simulations to actually calculate this. And this is a very good idea for a number of reasons. So if we run the Green-Kubo molecular dynamics simulations, we actually capture all orders of anharmonicity and all contributions to the heat current. So we don't make a lot of approximations when we do these calculations. However, converging these simulations is extremely difficult. And there are a number of reviews that actually just focus on that to actually provide the best way of converging these MD simulations. So what we would like to do is to have a lattice dynamics implementation of the Green-Kubo approach. So we want to have an approach that that captures the non-Lorentzian line shapes, but it is easy to converge in principle, and it is easy to interpret. So we are going to do that next. So the Green-Kubo method. So let's first discuss quickly the Green-Kubo in molecular dynamics simulations. So this is the expression for the lattice conductivity in Green-Kubo. Green-Kubo approach in the classical MD. So you have the correlation, the integral of the time-dependent heat autocorrelation function. So we integrate from 0 to infinity this heat autocorrelation function. And now the definition of the heat current can be different, and it is implemented differently in the different codes. But one of the definition of the heat current is given here, and this is I think this is taken from the LAMPS documentation, and the LAMPS is one of the most widely used MD codes out there. There is an interesting thing here. So this EA is the local energy, so the energy associated with the atom A. And immediately you can see that there is a problem if we are trying to run the DFT, because DFT does not have unique way of actually assigning energy to a particular atom. So for a long time, the ab initio and the calculations of the lattice-thermal conductivity using Green-Kubo and D were not possible, but recently there has been proven that there is a gauge invariance that allows you to use Green-Kubo and D. But one still needs to converge with respect to the length of the MD simulation, so you cannot run this forever, and you have to converge with the length of the simulation. The maximum correlation time. So what is the maximum correlation time? So here, as you can see in this integral, we go to the infinity. This is obviously not possible in the numerical simulation, so you have to actually end your simulation at some point. And so here we have some finite time tau, and then you have to converge with that number. And another one, extremely important thing that you have to converge with is the size of the supercell. And obviously, this limits the applicability of the Green-Kubo calculations. There are ways of actually going around the time constraint of the Green-Kubo, but it kind of involves biasing your result, and then you have to be very careful about that. Yeah, so as I said, very difficult to actually converge. Okay, but now we want to do the Green-Kubo in the lattice dynamics approach. So we again start from the Green-Kubo expression, but in the quantum limit. So it's basically the same as the Green-Kubo Green-Kubo formula that we had on a previous slide, except that here we have the different definition of the heat current, which kind of changes the prefactor here, but we also have here, instead of the time, we have the time plus is, and this part comes from the fact that we are not having the functions anymore, but we have the quantum operators. So, so we have to take into account that part. And the first thing that we have to do is to actually take some definition of the heat current. And in this case, we are going to take the definition of the heat current given by Hardy in this reference here. He derived this from the energy conservation law. And the definition of the heat current is given on this line. As you can see, it's quite similar to the definition that we had previously. And indeed, we are going to show in the next slide that they are actually identical to some approximation. But what are the ingredients? So here we have the sum over of phonon wave vector q and the phonon branches s and s prime. We'll need phonon frequencies omega qs, and we will need a generalization of the group velocity, which is actually now taking a form of the matrix, not a vector, for each phonon mode. And then we have these two operators, A and B, which are just the scale, displacement, and momentum operators. They are time dependent. And they can be expressed through the phonon annihilation and the creation in this way. So the small a and a dagger are the phonon annihilation and phonon creation operators. So we put this definition of A and B inside of this heat current, and then we disregard the combination of phonon creation and annihilation operators. So we disregard phonon annihilation, and phonon creation terms, and then we end up with the parallels heat current definition that we had previously. So we can use here, we can continue our derivation using this definition of the heat current, but we are not gaining pretty much anything by doing that, so we are going to keep this full expression of the heat current. Okay, so what we do next is we substitute this definition of the heat current to Green-Kubo formula, and as you can see, we are going to end up with the two-phonon Green's function, which involves the 4 phonon operators. Okay, and now we have to deal with the two-phonon correlation function, but we don't want to do that because it's difficult. And then what we do in that case is to decouple this two-phonon correlation function into the products of one-phonon correlation functions. So basically, we just take all possible combinations of the two operators here. The equal time correlation functions, because they are a combination of the position and the momentum, they are 0. So this part we disregard, and then we are left with this sum of the products of one phonon correlation functions. And again, just to reiterate this one phonon correlation function, especially this displacement, we already talked about it when we discussed the scattering experiments. And so this thing is basically the same stuff that we have talked before and that Antonio was talking 2 days ago, and Rafael, and everybody else. So now to make the notation easier, we are going to use shorthand notation for these correlation functions, and we are going to skip writing these cumbersome indices of phonon modes. Okay, so how does okay, another important point here, we are going to, because here we have the integral over time, what we are going to do to get rid of it is to go through the frequency space. So we are going to do the Fourier transform of these correlation functions. Okay, and then we get this expression for the lattice-thermal conductivity. And as you can see here, we are keeping the sum over 2 phonon wave vectors and 4 phonon branches. And we have here the already mentioned decoupling form of the two phonon correlation function. Okay, so here, as you can see, we will have to calculate 4 different correlation functions, right? CAA, CBB, CAB, and CBA. And in the previous talks, we only got the CAA. But since the time evolution of this operator is governed by the Heisenberg equation, and the position operator commutes with the higher anharmonic terms, we are left with very simple connection between time derivative of the position operator and the momentum operator. And of course, if we take the Fourier transform of this, we then get a linear combination between A and B, which allows us to express CAB, CBA, and CBB through correlation function AAA. So we only need CAA. Another important point here is that in the previous days, we have been only talking about the phonon spectral function, which I don't know if anybody used this notation, but here the phonon spectral function I will call sigma QS. And the dependence or the connection between this correlation function and the phonon spectral function is this one. So basically, they are the same except for this Bose-Einstein condensation, the Bose-Einstein population factor here. Okay, so we substitute this expression for CAA into this equation, keeping in mind the various ways these other correlation functions depend on CAA, and we get the final definition of lattice thermal conductivity in the Green-Kubo approach. And as you can see here, we are only having the sum over one phonon wave vector and two phonon branches. Again, we have the phonon frequencies and the phonon group velocities, and we have this integral, which is actually the main part here. And here we have the phonon spectral function. So to get the lattice conductivity, we integrate over phonon spectral functions, which means we take into account these non-Lorentzian dependence, the non-Lorentzian line shapes of the highly anharmonic phonon modes. And this allows us to be confident that this approach is actually useful even in the case of highly anharmonic materials where this phonon quasi-particle picture may fail. So you already have seen this definition of the phonon spectral function. So basically it's the Lorentzian line shapes. And also here important point is that because we use the Fourier transform at some point, we have here the integration from minus infinity to the plus infinity. So we have to make sure that we actually have the both poles included, so the positive and the negative pole of the phonon spectral function. And also, I think Raffaello was already talking about this ZQS function, which is defined through the phonon self-energy. Okay. And the expression for the phonon self-energy is this one. This is something that you have seen in the previous days. Okay, here we have a slight technical, just a small technical comment. So how do we actually calculate these things? These expressions, they are, so as you can, if you remember, Raffaello was talking that here it's not omega, but actually omega plus some small complex number. It's plus IE. So we have to add here plus IE. And if we just add this smearing parameter, we don't have to do anything else. We can calculate this expression in that way, and then we get something that is usually referred in the literature as the Lorentzian smearing, because we have the Lorentzians here. However, we can use this identity to actually split this phonon self-energy into the real and imaginary part, where the real part is the principal value of this integral, and the imaginary part it has this delta function. And now that we have the delta function, we have to somehow approximate it in the numerical procedure, and we are going to use the Gaussian function, and then this approach is called the Gaussian smearing. So there are two different ways of dealing with the poles in this thing, but in both cases you have something called the smearing parameter, which is a convergence parameter during the calculation. Okay, so this is the phonon self-energy, and again, just to show you again the final expression, because we are going to now discuss the two main parts. So here we have the sum over two phonon branches, and we can actually split this then expression into diagonal and non-diagonal parts. So the part where the S is equal to the S prime, and the part where the S is not equal to the S prime. So the first one is the diagonal part, where the phonon branches are the same. And what we have found and what we would expect it to be is that in the low anharmonicity limit, this expression reduces to the single relaxation time approximation, or the relaxation time approximation solution of the Boltzmann transport equation, basically the stuff that we got previously in the section Boltzmann transport equation. So what we mean by the low anharmonicity limit, so we are, for the low anharmonicity limit, I will refer as a situation where we have that the real part of the phonon self-energy is zero, so you don't have the shift of the phonon quasi-particle, of the phonon quasi-particle energy. And then the imaginary part of the phonon self-energy is a small constant number. So you lose the dependence of omega, and if we lose the dependence of omega, obviously, we get that our spectral functions are just the Lorentzians. Now that our spectral functions are Lorentzian with very small line width, we can imagine them being as the delta function. And so we have here one of them is the delta function. And what does delta function do to the integral? It kills the integral and replaces all the integration variables with the real part of the z function, which in this case is just omega, right? Because the real part of the self-energy is 0 in this limit. If we do all of this, we have to be careful about the sign of the imaginary part. So we want our spectral function to point up, so to be positive. And if we take care of all of that, we have this expression for the lattice thermal conductivity, right? And from this expression, we can see that the phonon, and if we compare this expression to the one from the Boltzmann transport equation solution, we can see that the phonon lifetimes is equal to the 1/2 imaginary part of ZQS, which is basically what Raffaello told us yesterday, and something that we could see from this expression of the spectral function as well. So, yes. So this is the phonon lifetimes in this limit. The second part of the expression of the lattice thermal conductivity is non-diagonal part. So the part where phonon branches are not equal. And this part has been for a long time neglected in the calculations. But recently it has been shown that this part describes a wave-like transport, which is significant in amorphous materials and complex crystals. And this is something that we you saw on one of the talks from yesterday. So in the case of amorphous materials, this type of transport is important. Obviously, because now we have different S and S prime, which have different frequencies, you cannot really do the same trick as before in the diagonal part. So we cannot approximate one as we cannot approximate one of the spectral function as a delta function. And it's much harder to actually interpret this part and compare it to the other approaches in the literature. But we can see that in the case that the S and S prime are different, this integral will have a contribution only if there is a significant overlap between phonon spectral functions. And when can we expect it to have a large overlap is at least either when the phonon spectral functions are very broad, so they spread over a large frequency range, or they are very close together. So we can expect it either when we have a bunching, which is in these complex crystal and amorphous materials, or when we have the highly anharmonic materials. Okay? So this is what I said. So we can expect this type of transport to have a contribution when there is a large bunching of phonon modes or large non-Lorentzian or large broadening of the phonon spectral lines. Okay. So are there any questions until this point? Because we are nearing the end and maybe it's better to actually start discussing. Yes?
Thank you. Well, it's when you were talking about the correlation functions, you had this T and then T minus IS.
Yes.
Yeah.
This one.
So it's the IS thing that is not or imaginary. What it is wasn't very clear to me where that sorry where that term is coming in.
Yeah. So this term appears from the fact that we have a these things are not functions; these are operators. So the time evolution of the operator is governed by the Heisenberg equations, and then once you actually try to calculate this time evolution of this operator, you end up with this term. It is not as easily to show, but yeah, it is from the fact that the time evolution of the operator is governed by this equation. And you have here the ensemble average, and from the ensemble average from the left and right with this where is it? From this Hamiltonian, you get the energies, and from those energies are actually what you get here, the S part.
So it's a bit like you're adding an imaginary part to the time, like because wait.
So I wouldn't be comfortable with saying that.
Yeah.
Yeah.
Okay.
Yeah. I'm not sure if there is a physical meaning of that.
I have one more question. If you go to a few slides, next,
Yeah.
where you're talking about the C, the A and B,
Yes.
that one. You sort of the red one. Why that one?
Yeah. So basically, it's because they are equal time, right? So these things are time dependent. These things are time independent. And then when you do the ensemble of a property and its derivative, they have to cancel out. Always. Yeah. So here they are evaluated at the time equal to 0, and here they are evaluated at the time equals t. So they are at the same time, so they have to be 0. So if you think about this is a position, this is a velocity, this type of ensemble average is always 0.
Yes. Yeah. It makes sense now. Thank you.
Maybe not know if I'm mistaken, but probably the imaginary part that comes in that equation is related similarly to what happened in part integral program, is that you have you are doing ensemble averages, so you have a term in the trace of the density matrix, which is a to the beta Hamiltonian, and this is plays the role like it is an imaginary time, no? Okay. In an evolution.
Yeah, so it's like
So in fact, you integrate the integral from 0 to integral in ds, you are integrating this imaginary time, which is the temperature, no? So
It is come from the fact that the time evolution and the ensemble average both are e to the something, and the ensemble average is not imaginary factor, and the time evolution is. So that is why here is I. Yeah, but it's not imaginary time. That's not.
So when you define here in this slide the heat current,
Yes.
you are using the operators A and B.
Yes.
But I don't see the difference because they both includes the creation and annihilation. And if you could explain it again, like the difference between both operators.
Yeah, I mean the definition. So what are the phonon creation and so it is other way around. So we are not defining. We are not defining phonon displacement and phonon momenta through these. We are actually defining these through the phonon momenta. So when you have a Hamiltonian, which is basically the harmonic part of the Hamiltonian, which is a kinetic part plus the harmonic interaction, you want to diagonalize it. And when you diagonalize it, you get the phonon creation and annihilation operators, and that diagonalization procedure gives you this relation. So it's other way around.
So it would you start from phonon annihilation and creation, and then you obtain.
No, you start from the displacement and momenta, and then you get phonon creation and annihilation operators through the diagonalization procedure.
Okay, thanks.
Thank you for the talk.
Yeah.
I have always a question about introducing the strong anharmonicity in the spectral function. It's surely a part of the correction, and surely must have that solution. But in the energy flux, there should be also addiction to the energy flux.
Yes.
Because at the moment we are using the harmonic energy flux, but then the operators in that are stronger anharmonic. Have you ever tried in molecular dynamics to evaluate the extra part of the anharmonic energy flux? I think there is a package EPI that gives you all the contribution of different orders.
Yeah, you're right. So there is I don't know if I call it inconsistency, but there is a fact that here we are using the harmonic part of the heat flux, so we don't have the anharmonic contribution to the heat flux. But we are later on adding the anharmonicity onto the spectral functions. Yeah, in the molecular dynamic simulations, you could actually do that. You could take your harmonic plus you can take the full heat current, which is defined as this, or something similar to this, and then split that one into harmonic and anharmonic part. And this has already been done and discussed. What are the conclusions of that? I don't really remember, but one can do that. Here, obviously, why are we keeping only this term is because this term is complicated enough. So we cannot do anything better. And until this point, I'm not sure if we ever found a system where the anharmonic correction to the harmonic heat flux is actually of any significance. I'm not sure, but I have never seen that somebody discussed that in this approach. Yeah, there are tunnel ones.
Thank you for the lecture. What's the advantages of using lattice dynamic methods with SSCHA compared to MD methods in calculations of thermal conductivity?
Yeah, so, well, so here, obviously, it's actually how expensive two different methods are. And the MD is usually more expensive. I use the MD and I'm extremely uncomfortable with the convergence criteria that we have to use to actually calculate MD. In my opinion, the simulation lengths that you have to go through to actually converge the MD simulations are not possible with the ab initio MD. Again, I said that there are ways of actually doing it. It's just that I'm not comfortable with those procedures. So that's one advantage of using this phonon-like picture to the MD. The other one is when you calculate the heat current in the MD, you get the heat current and you get the number for the lattice thermal conductivity, but you don't have any way of actually analyzing it. So you don't know which phonon modes contribute the most, and then obviously you cannot know how to actually design your material to improve its performance. While in this approach, where I have phonon modes, I can actually say I can stop this phonon mode if I make the the crystal grain this size, or I can put this type of imperfection inside the crystal, and this will scatter the most heat-carrying modes. In the MD, that's not possible. Obviously, MD has different advantages. So in this approach, I cannot break the translational symmetry of the crystal, while in MD, I can put whatever I want and calculate the heat current. So those are basically the ones that I can think of on the spot. And that's actually a good way to actually continue with the talk. So we can compare the Boltzmann transport equation and the Green-Kubo, but here I'm comparing the Boltzmann transport and the Green-Kubo from the lattice dynamics, so these two methods that I have been talking previously. The important thing is that, well, one of the important things is that at the low anharmonicity material, so in the limit that I was talking before, both materials give the same result. And I hope that in the hands-on session you will see that this is true. Also, in overdamped regime, so the regime where your phonon spectral functions are not good quasi-particles, the Green-Kubo is still applicable, while Boltzmann transport equation we don't know. There is no reason to believe that the Boltzmann transport equation still works, but in my experience it does, so don't worry about that. For the speed, the Green-Kubo method, because it has to calculate the phonospectral functions on the grid of energies, is usually slower, is not usually, it's always by definition slower than the Boltzmann transport equation. Implementation of the additional scattering mechanism is more straightforward than Boltzmann transport equation, because in Boltzmann transport equation you basically only have phonon lifetimes, and the good thing about that is that you have the Mathiasen rule, and whatever type of scattering you want to add, you just add it through the Mathiasen rule, and then you have that these additional scattering mechanism, like the grain boundary scattering or the scattering from the impurities. While in the Green-Kubo, you would actually have to get the frequency-dependent self-energy for each of those scatterings, and maybe even the crossing terms between the anharmonicity and that. And another important regime that I have not been discussing here because it's usually not important for the highly anharmonic materials, but we had a talk yesterday that says otherwise, is the hydrodynamics regime, so which is usually important at very low temperatures, and this regime is more easily handled in the Boltzmann transport equation. So in Boltzmann transport equation, what you need to do is basically solve it self-consistently, and you get these numbers, while in this case, in the Green-Kubo approach, you cannot do the decoupling scheme that we have been using, and that made our life much easier. Okay, so this is the comparison between BTE. So the bottom line is, if you don't have a potato type of spectral function, you are safe to use Boltzmann transport equation. And if you have it, you run the Green-Kubo and you just compare them. And see what are the results. Okay, so the implementation in the SSCHA code. So this is something that we are going to go through on the hands-on session, but this is just a small preview. And actually, this type of methods or this type of algorithm or whatever you want to call it that I outlined in the previous slides is applicable for any type of parameterization of your Born-Oppenheim energy surface or the phonon picture. But here, why is it good at the SSCHA? Well, the SSCHA gives temperature-dependent second and third order force constant, which are renormalized by the anharmonicity, which usually means that they are much easier and much more suitable for this type of calculations, because in my experience, once you use SSCHA, you get more short-range interaction. So your Fourier interpolation works much better in SSCHA and other non-perturbative methods than if you just calculate it from the analytical type of approach to force constants. So the thermal conductivity calculations are implemented inside the thermal conductivity object in SSCHA. And we can use the single relaxation time approximation solution of the Boltzmann transport equation or the Green-Kubo method to calculate lattice thermal conductivity. I guess if there is a significant interest in this, we can improve these calculations by adding bells and whistles to it, but at this point we only have these two methods. And also there are obviously a number of functions that you can use to actually analyze the results. And again, this is something that hopefully will be guided by the user base and what they say that it's useful to them. Okay, so to do Boltzmann transport equation solution, what we need are phonon group velocities, phonon frequencies, and phonon lifetimes. And the phonon lifetimes, as has been discussed by Raffaello in previous days, can be calculated in 3 different ways. Well, he was talking about the phonon line width, which is basically just inverse phonon lifetime. The first way is the perturbative, which is the one that is identical to all the other codes that calculate lattice thermal conductivity, where we have the imaginary part of the self-energy to be inversely proportional to the phonon lifetimes. So this is the perturbative part. Also, there is a Lorentzian approximation. So the Lorentzian approximation is the one that we got from the low anharmonicity limit. And this is the one that is actually implemented in SHA as a default. And these two are practically the same in the low anharmonicity limit, but you can see some differences, minute differences, if the anharmonicity is large. Another way of actually getting the phonon lifetimes is to solve this equation self-consistently and then calculate the phonon lifetimes, not at the SHA auxiliary frequency, but actually at this self-consistent solution of this equation. And also, you can calculate this coherent transport, or whatever you want to call it, the one that's important for the amorphous materials and the complex crystals, based on these 2 different approaches, which should give similar results. It is actually interesting that these 2 results are different from each other, and they are differing from this this Green-Kubo approach as well. So, yeah. In the Green-Kubo method, also the calculation of it is implemented here. Again, there's no hydrodynamics in this method, so it is equivalent to the relaxation time approximation solution of the Boltzmann transport equation. And the spectral function at this point are calculated in the dress dynamical bubble approximation, so you don't have the 4th order scattering yet. And the spectral functions are sampled on a frequency space. So we have to solve this integral. Where is it? So we have to solve this integral, and we have to solve it numerically. So we take this range of frequencies from -2 omega dBi to 2 omega dBi. Why omega dBi is because that's where you can have the ghost showing up in the phonon spectral function. Yes, with the number of NE frequency steps, and then you have to actually converge with the number of these frequency steps. And here, the problem obviously here lies that the step between neighboring frequency steps in the integration of the spectral function has to be smaller, or at least comparable to the lowest phonon line width. Otherwise, if it's too big, you're just going to skip your phonon spectral function altogether. So it has to be sufficiently small to actually see the whole phonon spectral functions. Obviously, this is a problem if you have highly harmonic materials which have very small phonon line widths. That means that you have to use a very large number of these frequency points, which slows down the calculation. Yeah, that is all that I have prepared, and thank you for your attention.